We have here learned how to simplify series or parallel impedances as well as series and parallel admittances. Okay. And, okay, let's do some example here. For example, here we have the voltage source having an amplitude of 60 and a phase angle of 45 degrees. Find the admittances, the parallel admittances here, and then the current. So first we find the admittances from the impedances shown for each of the branch. Yeah. Yeah. So then the admittances will be, if a branch is just addition of the two admittances. So YR plus YL. So this is will be 1 over 2 or half. This is 1 over J4. Or if you multiply with J and J becomes minus J divided by 4 or minus 0.25 J. Yeah. Then the ZP is the inverse of this. Yeah, the inverse of this admittance. Yeah, 2 times 2 cross 2 times J4 plus 2 plus J4 times YP. Okay, so this is to simply make it as yeah, this is 0.5 minus J times 0.25 Siemens. Okay, so this is if we want to calculate from the ZP. Okay, then the current will be equals to the admittance multiplied by the voltage. So or this one 0.5 minus J 0.25 times the voltage is 60 with the phase angle 45 degrees. So this is not yet operable, right? Because one is still in the complex form and the other one is already in Phasor. So we have to change this into Phasor format. Find the magnitude, yeah, by the magnitude by this square plus this square, then the square root, and the angle of this admittance by arctangen of minus 0.25 divided by 0.5. So this will result in the magnitude to be 0.559, yeah, an angle of negative 26.565 degrees times this. So the current magnitude will be this 0.559 multiplied by 60, and the phase angle of the current will be minus 26.565 plus 45 degrees. And we obtain this one. Okay, another example here, we have a voltage source of 10 with a phase angle of 20 degrees volt, yeah, and connected to parallel branches of resistors, inductance, and capacitor, and another resistor. So the YP will be equals to the additions of the admittance of each of the branch. Okay. This is 0.5, this becomes minus J 0.5, this becomes J1, and this becomes 1 over 4 or 0.25. And we obtain 0.75 plus J 0.5 Siemens. Then we convert this into Phasor form. Yeah, to find the magnitude here, we put this square root of this 0.75 square plus 0.5 square. We obtain 0.9014. The phase angle is obtained by arctangen of 0.5 divided by 0.75. Thus, we obtain 33.69 degrees. Then the current can be calculated by the admittance multiplied by the voltage. This value multiplied by 10 with an angle 20 degrees. So the magnitude is 0.9014 times 10 or 9.014. And the phase angle becomes this plus this, so 53.79 degrees. So if you see from this example, the use of Phasor really simplify the calculations. You do not need to, especially for steady state analysis, you do not need to use differential equation to find the solution. So here, this is now example of reducing complex network by using series and parallel reduction. So first we can simplify this, finding the new impedance by using the parallel impedance formulation, J4 times minus J2 divided by J4 minus J2, and we obtain 8 over J2. Then, or alternatively, we can use admittance formula here, so become minus J 0.25 plus J 0.5. We obtain J 0.025. From here, we calculate the impedance by inverting it. So Z4 equals to 1 over Y4 or minus J4. So here then we start with as a series. We can simplify by immediately adding the 2. Z3 equals to 4 plus J2. And this also in series now. And this is first, we calculate first here in series 2 ohm plus J6 minus J2. So becomes 2 plus J4. This is in parallel, so we calculate similar like this. And then we obtain Z1 equals 1 over J plus 0.5. And this we need to process again. So usually the denominator should be real, all real. So we multiply this with 1 minus J 0.5 divided by 1 minus J 0.5. So the denominator part becomes 1 plus 0.5 squared. And then we obtain real part and imaginary part. So from here, then we have Z1 from here, Z2 here from this series as impedances. We have Z3 here and Z4 here. Z3 and Z4 can be further simplified. So Z34 equals to this plus this one. So this equals to 4 minus J2. Okay. Then Z2 and Z34 basically are in parallel. So we can obtain the parallel impedances as Z234 here, Z2 times Z34 divided by Z2 plus Z34. And we obtain 3 plus J1. And finally, this is Y2. Y2 is this one. This is another way. So instead of using the formula for parallel impedances, we can use the formula for parallel admittances. But first, we need to calculate the admittance for this branch Y2 and also the admittance for 3 and 4, Y3, 4. By inverting it, then we do addition, and then we make another conversion. And so this is Z234 is the inversion of Y234, like this. And finally, the equivalent impedance will be equals to Z1 plus this Z234. So 0.8 plus 3 becomes 3.8 plus this one J1 minus 0.4 plus J 0.6. This is in complex format. And then if you want to have it in Phasor format, we find it the magnitude by 3.8 square plus 0.6 square, then making a square root of that sum. Then we will obtain 3.847. The angle we calculate by arctangent of 0.6 divided by 3.8, and we will obtain 8.973 degrees. Okay. So this is learning extension. Find the impedance ZT here. This is, I think I will skip this, so you may later see the slide and then review by yourself. I think this is the same way of like in the previous slide. Okay, so now we are going to go to a new section, which is about phasor diagrams. So this is where we display all the relevant phasors on a single or a common reference frame. So this is if we want to see the to visualize the phase relationship among the variables. For example, between the voltage and current. Actually we have seen it, we have shown it in the slide here about phasor, where, for example, with inductance, the voltage will lead the current by 90 degrees using a phasor diagram. Or in capacitance circuit, then the current will lead the voltage by 90 degrees also. So how to visualize this? This by using phasor diagram. Sketch, for example, the phasor diagram for this circuit. We have a current source IS connected to a parallel circuits of branches here with R, L, and C, each with its own impedance. Yeah, R, J omega L, and this one is 1 over J omega C. Any one variable can be chosen as reference. Let's say for this case, we select voltage. Using KCL, so IS equals to the voltage divided by R, current here, IR, plus voltage divided by the impedance here in the inductance, voltage divided by J omega L, then voltage divided by the impedance in the capacitance, or J omega C times V. So here we see that the voltage divided by R does not add any J to the current. So the IR here, the IR here in this branch will be at the same phase with the voltage. The capacitance, the current flowing through the capacitance, on the other hand, has a factor of J omega. So there is a J here, so which means it will add the phase angle by 90 degrees. So we draw in the phase diagram the IC, yeah, perpendicular to the positive y-axis relative to the phasor of V. Yeah, the V is become the reference here. The current flowing through the inductance IL equals to the voltage by the J omega. The J is in the denominator, or basically it means that it's subtracted. So the IL is lagging the voltage by 90 degrees. So we draw the IL towards the negative J direction. Okay. So if the current IL here is larger than IC, what will happen is then the reactance, the current due to these reactances will be more tend towards the inductance part. So will be go more downward here. So then the resultant IS will be in the this quadrant, yeah, which means that the IS is lagging from the voltage by this angle. If, however, IL is less than IC, IC is larger in magnitude compared to IL, so we have the IS resultant, yeah, will be more in the positive quadrant here. Okay, so it means the current will lead the voltage by certain phase angle here. So in summary, when a network is capacitive in characteristic, the current will lead the voltage, yeah, in phase angle. If the network is inductive in nature, the voltage will lead the current. Yeah, to remember it easily, just remember the formula that in inductive voltage will be equals to J omega Li, right? So this additional voltage means voltage lead the current by 90 degrees. So the current is lagging here, like in the inductive circuit. In the capacitive circuit, voltage equals to current divided by J omega C, or minus minus J I divided by omega C. So here voltage is lagging from the current by, because this is minus J, by 90 degrees. Okay, this is to remember. So you can remember it by using the formula of impedance for capacitive and inductance to determine if if you forgot, yeah, if you haven't forgot whether capacitive is, which one is lagging or which one is leading, voltage or current. Yeah, that's why this is what Jesse was asking during the quiz, whether we can have voltage and current leading or lagging. Yeah, yes, this is the application of what you have learned in the sinusoid section. So this is an example. Do the Phasor diagram for the circuit. We have a voltage source connected to a series of resistor, inductance, and capacitor. Yeah, resistor is 4 ohm, inductance is 15.92 millihenry, capacitance in 1300 to 26 microfarad. The radian frequency is 377 per second. So we can calculate VR first, equals to Ri, VL equals J omega Li, Vc equals to 1 over J omega C times I, and Vs equals to VR plus VL plus Vc. Let's check the current now here as the reference. It means we put the current in the x-axis, yeah, positive x-axis. Yeah. So we draw the old phasor. As we can see here, in the VR will be in phase with the current because no addition of phase angle due to J. Okay. Yeah. VL on the other hand is leading the current by 90 degrees. That's why we draw the VL inductive upward in the vertical y direction, positive y direction. Vc is 1 over j omega ci or equals to minus j I divided by omega c. So it means the voltage in capacitance is lagging the current by 90 degrees. So we draw the Vc in the negative y-axis. If VL, the voltage L here is larger than Vc, then what we will have, the Vs, the resultant will be inductive, right? In the inductive region, in this positive y-axis region. Let's put the non-numerical values. The VL is j omega Li. This is 6, and the VR here is 4 times the IM, the current IM. Here 6 comes from the 15.92 multiplied by 377. Yeah, 377. This is in millihenry, yeah, times 377, we obtain 6. And Vc we obtain from here 1 over omega c minus 90 degree, 1 over omega c, 1 over 377 times 1336 in microfarad, we obtain here 2. So in this case, we see that VL is larger. Yeah, VL minus Vc equals the magnitude of VR. Yeah. 6 minus 2, yeah, equals to 4, right? So VL here is larger than Vc. That is why the current, the voltage is leading the current by 45 degrees angle. Yeah, if we put the diagram Vs as reference in the vertical way, then we will obtain, we can calculate Vs as 12 over square root of 2 with an angle of 90 degrees, okay, from the x-axis. And this becomes like this. Yeah, VL is in this like 90 degrees, 45 degree, yeah, from Vs, and the current is minus 45 degree from the Vs. But Vc is in the minus 90 degree from the current. Okay. The voltage R, yeah, so will be equals to 12 with a phase angle of 45 degree. Yeah, 12. The current will be equals to, in this case, 3 with a phase angle of 45 degrees. And the Vc, 6 with a phase angle of minus 45 degrees. And VL, 18 with phase angle of 135 degrees in volt. So you can have it like this, yeah, as this is the when we put current as the reference. But now when we want to put, after we find Vs, we want to put Vs as the reference with the in the vertically upward, yeah, with in the positive y-axis. Let's say do some one example again. Find the frequency at which the Vt here and It are in phase. So because as we see here that this relationship, the phase angle is related to the omega value. Omega is related with the frequency. Okay, so in this problem, particularly the question asks us about to calculate the frequency where Vt and It are in phase. So it means uh, Vc and Vl should be in the same value, right? They cancel each other. So for example, if the Vt here is 1 with an angle 0°, yeah, a phase angle 0°, and capacitance 1 microfarad, inductance 1 millihenry, resistance 1 ohm, yeah, the phasor It and Vt are collinear. So using KVL, because Kirchhoff voltage law, voltage equals to the current uh, multiplied by the admittance. Yeah. Yes, which is 1 over j omega c. Sorry, multiply to the divided by the impedance. Multiplied to the impedance. Then inductance here j omega li, and the resistor part VR equals to Ri. Okay. So now current was chosen here as the reference. Current here as the reference. Okay. So the voltage will be equals to the voltage of R here equals to Ri is in phase with the current. And the resultant here voltage equals to the this part 1 over j omega c I, which is since the capacitive voltage is a negative j here, so it is drawn downward, yeah, to the negative y-axis. While the inductive voltage has a j, positive j, so it is drawn with relative 90 degrees to relative to the positive x-axis. So from here, this is only collinear. V will be collinear with current if and only if this equals to this one. Cancel to each other. Yeah? So j omega L plus I divided by j omega C should be equals to 0. Okay. So here, from here, then this move to the other side, negative. Yeah. Then multiplied denominator, so becomes j square or minus. This is already minus, so become positive. Omega square LC equals to 1. So omega square equals to 1 over LC. Omega equals to 1 over square root of LC. Okay, so omega square here from 1 millihenry plus time multiplied to 1 microfarad, we obtain 10 to the power of 9. And this is omega square, so the omega equals to 3.162 times 10 to the power of 4 radian per second. So the frequency will be equals then this omega divided by 2 pi. So we obtain 5,000 hertz. 5,033 hertz. This is the frequency where the voltage and current will be collinear, or there is no phase difference. Another example, draw a phasor diagram illustrating all voltages and current here. Okay, so we have current source here with magnitude 4 with a phase angle of 45 degrees, flowing through 2 ohm resistor I1, flowing through the minus J4 capacitance I2. So I1 will be equals to the volt here. So using current divider, formula here. So minus, remember in the semester 1 current division formula, minus J4 divided by 2 minus J4 times the current. So here then we change this into phasor format. So this becomes 4 minus 90 degrees. So this we have to calculate. the magnitude from this square plus this square, and then putting square root on it, we should obtain 4.472. The angle is found by arctangen of -4 divided by 2, and we should find this one. So by this, then it is easy to calculate the I1 magnitude. So that's 4 times 4 divided by this, and the phase angle will be -90 degrees plus 45 degrees, negative 63.45. Okay, then we will obtain 3.578 with a phase angle of 14.435, 18.435. The I2 similarly can be calculated using current diffusion formula. Here this is 2 actually, 2 minus 4. This is supposed to be 2 ohm, this one. Okay, this is that one, this is 2 ohm. So from here it equals to phase angle 0, and then this also we convert similarly like this, and we will obtain I2 equals to 1.789 with this angle. Yeah, so here we calculate using voltage current divider formula also. It's simpler rather than if we subtract I1 from this I to obtain I2. Yeah, if we have I1 here, so I2 will be equals to 4 with 45 degrees, negative 3.578 with an angle of 18.435 degrees. Then we cannot operate it directly. We have to convert them first into complex format. Yeah, so x plus I, ji, x plus jy. Okay, and that is more tedious. We have to calculate, etc. for both I and I1. The simpler method is using this current diffusion formula. Although both ways will produce the same result. So the voltage will then here be equals across to 2 times I1, 2 times this part, or so if we then withdraw the phasors or are known, we need to check the reference. So the voltage is 2.16 here with an angle of 18.40 degrees. So the current I1 is 3.5, the same angle as the voltage, right? In phase with the voltage here, I1, 3.578 with an angle of phase angle of 18.45 degrees. The current I here is 4 ampere with a phase angle of 45 degrees. Then I2 is 1.79 with a phase angle of 180 degrees. So this is the phase diagram. Okay, any questions so far before we continue to the next section? We still have time. No questions? So everyone's ready for quiz, yeah?
No, sir.
No, sir, no.
Doesn't mean ready, sir.
No question means understand, right? Understand all. Okay, that's so means maybe we will have the quiz next week, because we don't have much time for remaining time in this hour. Let's just move forward to the next section. So, which is to use Kirchhoff laws for this AC steady state analysis. So basically, now we have the voltage, we have the current, similar like DC analysis, but of course the difference is then the voltage is in the phasor form, the current also in the phasor form. It's a certain frequency in sinusoidal function, a certain phase angle. Okay. We have also derived the impedance and admittance for resistor, inductor, and capacitance. So for simple circuit, then we can use what we have learned in semester 1, which is Kirchhoff's law, and the other law as well, Ohm's law. And later, for more complex circuit, we use node analysis, loop analysis, superposition, source transformation, definite in Norton's theorem. The difference is that if in the semester 1 you learn it using just resistor, now you use impedance. Semester 1 you use conductance, now you use admittance. Okay, which can be different based on whether it is resistor, capacitor, or inductor. So for relatively simple circuit, we use Ohm's law for AC analysis. Okay, that is the voltage equals to current times the impedance. Then you derive the rules for combining the impedance and admittance. Use KCL, Kirchhoff current law, and Kirchhoff voltage law. We have used basically in the previous example current divider. Voltage divider can not no example yet. For later, for more complex circuit, we can use also complex analysis like node loop analysis, superposition, Thevenin's theorem, Norton's theorem, and source transformation. Let's give this a shot. Yeah, this is one example. Compute all the voltages and currents in the circuit. We have a voltage source here with 24 of magnitude and phase angle of 60 degrees, and connected to a resistor for ohm and inductance J6 ohm, the impedance, and the capacitance with minus J4 ohm impedance. Okay, the I1 is the current flowing through the 4 ohm resistor, the I2 is current flowing through the J6 ohm inductance, and I3 is the current flowing through the 8 ohm and minus J4 ohm capacitance. Compute I1 first. After that, we use current divider to calculate I2 and I3, and we can use Ohm's law to calculate V1 and V2. Okay. So here the Z equivalent for all of this, for all of this will be 8 minus J4. So this is basically the series admittance, series impedance in parallel with J6 ohm, then in series again with the 4 ohm part. So this will be 4. So here then we obtain 4 plus 24 plus J48 divided by 8 plus J2. Since we will obtain this, we make it into Phasor form. So 8 plus J2 we have changed into this form. In the upper part, the denominator part, we change into this. So the value will be 79.1696 divided by this to obtain this. And the phase angle will be 45 minus 14.036. Okay, then the current I1 will be equals to this voltage source divided by this equivalent impedance. Yeah. The 24 phase angle 60 divided by this value. And we will obtain I1 to be equal to 2.498 with phase angle 29.036. I3 equals to using current divider formula. So J6 divided by 8 plus 8 divided by 8 plus J6 minus J4, yeah, or 8 plus J2 multiply to I1. Yeah, so remember the current divider formula from semester 1. So then here I1 this value. So here we can convert to Phasor form. J6 becomes 6 with phase angles of 90 degree divided by 8.246 with a phase angle of 14.036. Okay. So I2 can be calculated as well using voltage division formula. Sorry, current division. Yeah, yes. So we will obtain the value for I2 like this. I1 is this one, and I3 here. Okay, and if we are asked to draw the phase diagram, it's like this. I1 has an angle of 29.06. I2 is 2.71 with an angle of minus 11.58, and I3 is 1.82 with an angle of 105 degrees. Okay. The voltage then, voltage 1 will be, you can calculate using Ohm's law, equals to I2 multiplied by 6, J6 ohm. J6 ohm or 6 with a phase angle of 90 degrees. V2 is similarly, you can calculate using Ohm's law. Here the minus 4 with the minus 90 degree phase angle from minus J4 times the current flowing through that capacitor, I3. So V1 equals to 16.26 here, what we'll obtain. So multiplied with this one, and this one is 4 with the phase angle of minus 90 degree multiplied by this, and we obtain this part. So as a hint that if you do multiplication or division operation in voltage, impedance, current like this, it's easier to use Phasor form. Okay, but if somehow you need to use addition or subtraction operation, it's easier in the complex form. X plus jy form. Usually when you need it to calculate series impedance or parallel admittance, something like that. Okay, so this one is if the V output here is 8 degrees, with an angle of 45 degrees, compute Vs. Now this is a backward calculation, so but the same basically. So V output here equals to I3 multiplied by 2 ohm, right? So from that Ohm's law, we can calculate I3. And using current divider formula, we can have I1. And first, we also have to find the equivalent impedance of all. And then by multiplying I1 with that equivalent impedance, we will obtain Vs. Okay. Compute I3, then compute V1. After computing V1, then we can have I2 and I1. I1 will be obtained from I2 plus I3. But actually, if you have I3 already, you can use current division formula to calculate I1. Reverse current divider formula. So no need actually to calculate V1. But okay lah, let's follow what is the instruction here. After that, then you can compute Vs. So I3 equals to V output divided by 2 ohm. So this 8 with angle 45 degrees divided by 2 ohm equals to 4 angle 45 degrees. Then V1 equals to 2 minus J2. V1 is the voltage here. V1 is the voltage here. So equals to the current I3 multiplied by the series impedance here, 2 minus J2. So from there, you obtain square root of 8. And then you convert again, because you do multiplication here. So to make it simpler, you convert this form, the complex form here, into Phasor form. It becomes square root of 8 with an angle of minus 45 degree times 4 times angle of 45 degree. So the value of V1 becomes 4 times square root of 8. The phase angle is 0, right? 11.314 with the phase angle of 0 volt. Then current I2 is equals to V1 divided by J2 here, the impedance. So we will obtain here 5.657 with phase angle of minus 90 degree. Then I1 equals to I2 plus I3. I2 here plus I3. Now, if like this, addition for operation, it is not that easy to calculate it using Phasor form. You have to convert this into complex form. If it is converted in complex form, this becomes minus J 5.657. This becomes this one. Yeah, you know, yeah, how to convert from phasor to this. Okay, so the component, the real form will be 4 times cosine 45 degree. The imaginary form will be j 4 times sine 45 degree. Okay. So from here, then you have the real form, the real component 2.828, the imaginary component here, j minus j 2.829. Then we compute Vs. Vs can be calculated by I1 multiplied by the equivalent impedance. Or yeah, Vs here equals to 2 ohm here I1, or yeah, directly with plus V1. This plus this voltage here. V1 is already known here, and 2I1 is here. So here we have to convert also this phasor form into complex format. So then we will, well, since luckily since this is have a zero angle phase angle, then basically this is already the real form. So this plus 2 times of 2, 8 to 8. So total becomes 16.97 minus j 2 times 2.829, yeah, 5 minus j 5.658. So this is the voltage source. We can convert it again to phasor format. Yeah. So like this is become 17.888 with phase angle of negative 18.439 degrees. Okay, so I think time is up. So I will conclude it until this slide, yeah, so that your heads are not blowing. Any questions so far?